Today, we will finish our basic concept, and then we'll go to the Fourier analysis. And you will know that why we need to learn Fourier analysis. Okay, but before we using that, we still need to know what vectors are. Okay, you probably have already learned that in the engineering mathematics, but here we have something new. For vectors, that x is a vector, x be a vector in the space, and we have a basis. Okay, so with a basis in 2 dimensions, it's like basis E1 and E2. Okay, suppose I have a vector x here. So x can be expressed as a linear combination of the bases. That is A1 E1 plus A2 E2. And the basis can be also known as orthonormal basis. So if we say that the basis is orthonormal, that means first, the inner product with itself is 1. So for all k, the norm square, okay, which is ek, inner product ek, it should be 1. So the norm square is 1. That means they are normal. The second one, for the orthonormal, your vector, if you have a different basis, like so k is not equal to L, then your inner product is 0. So if you, what does that mean if your inner product is 0? This means orthogonal. And orthogonal means you can't find the projection on each other. That's called orthogonal. So if your bases are normal and also orthogonal, then we said those bases are orthonormal bases. Okay, normal, so the inner product is 1. Ortho here, the orthogonal, the inner product with 2 different vectors will be 0. So suppose we have a vector x, that's the linear combination of your bases. Again, I gave this example many times. Suppose x is 5i plus 4j. How can I get 5? How can I get 4? To get this coefficient, for example, if to get this coefficient 5, I have a vector x inner product what? Their basis. Right? Because 5i plus 4j inner product I, then we have a 5. I inner product I. Because they are orthonormal, this one is 1. And then 4j inner product I, this should be 0. Because they are orthogonal. So to get the coefficient, you have your vector, inner product, your basis. So your vector inner product, your basis, then you'll get their corresponding coefficient. Here's the example. These two, first you need to check if this bases are orthonormal or not. Okay, but you can check that this is orthonormal because E1 inner product E1 itself, the vector inner product itself, it's 1. And also E2 inner product E2, that's 1. But their inner product with E1 and E2, that's 0. So they are orthonormal. Since they are orthonormal, suppose my vector is x1, x2. Okay, this is my vector. Then we know x will be summation ai, ak, ek. I want to find a1 and a2. How do I get a1? Actually, we know that x is a1 e1 plus a2 e2. Right? How do I get a1? X inner product e1. Right? So a1 is, we have e1, their coefficient, and x. This is e1. Then your coefficient is 1 over square root of 2 x1 plus x2. And then the coefficient a2 is 1 over square root of 2 x1 minus x2. Therefore, I can express x now. The x is a1. E1 and A2 E2. Now this is just a vector, okay, and we can also express the function as vectors. So here, the functions as vectors, we can think of a complex valued function as a vector. So we can do like vector addition, vector subtraction, or the vector inner product. So for example, the vector addition, so you add two functions. So for addition, it is just add the function. And for the vector inner product, okay, here's the definition. For inner product, okay, we use the integration. And here we have f times g conjugate. So here we have a complex conjugate. Okay, so this is the vector inner product. Right, if you don't have any questions about the vectors, now let's talk about the causal LTI systems. Okay, some people are still confused about what causal system is. Let's just talk about it. So what is the causal LTI systems? Okay, for continuous time, we have ODE. Or discrete time, we have a difference equations. So first, for the causal continuous time system, what does that mean, causal? If a system is causal, the output only depends on the current input and also the past. So the relationship between x and y, we can use the ODE to express that. So for example, like this. This is the causal continuous time LTI system. For discrete times, we have the difference equation. This is a difference equation. Okay, then why the causal LTI systems are important? Because we will see many practical implementation. Okay, we'll see that in 10 minutes. Okay. For example, if for the continuous time, system is defined by here. Okay, assume the system is causal, then you need to find the output when the input is this one, the exponential times the unit step function. Okay, so now let's quickly review our ordinary differential equations. So here, we need to solve the equation. Okay, we need to solve ordinary differential equation y prime plus 4y equals e to 2t times the unit step function. How do you solve this ODE? We need to set into two parts, right? Let's see if you really learned engineering mathematics well. How do you solve this ordinary differential equation? Yeah, we need a homogeneous solution. So homogeneous solution, that is also called the natural response. So for natural response, that is a solution of y prime plus 4y equals 0. You should get the y is c times the constant times e to the minus 4t. Then we need a particular solution. Okay, so the particular solution yp is a solution of y prime plus 4y equals e to the 2t and unit step function. So how do you find the particular solution? So how do you guess your particular solution in this case? Yeah, you could use Laplace, but intuition, from your intuitions, remember for the ODE, we always doing what? Yeah, we need to guess, right? So what is the particular solution here? Depending on here, so it should be like something with exponential, and also the unit step function. So we assume y let's see, yt equals constant times e to the 2t and times unit step function. Okay, then you take the derivation y prime and plus 4y, you should get 2a e to the 2t plus 4a e to the 2t. Okay, and that should be equal to on the right hand side e to the 2t ut. So you get a equals 1/6 So the solution, the overall solution, okay, general solution will be the first homogeneous or natural response plus the particular solution okay. And then for the constant C, how do we get the constant C? We need an initial condition. Okay, so how do you solve for C? Then we need initial condition. For example, you let y of 0 equals 0, then you can get the constant C. And you can see this output depends on where the input here, the current input, no future input or past. So it is causal or memoryless. So here you can also observe this is your input, and here is your output. This is the continuous time example. Let's see the discrete time. We have the difference equation. Okay, so the difference equation is here. Right, so for this difference equation, I also need a solution with the homogeneous solution and the particular solution. And then this homogeneous solution is that having all this equals 0, and then the particular solution will be the same. Maybe it is still a little bit abstract, but we have the example, the equation here. But you only have this equation, right? What does that mean? This ordinary differential equation. So here I just have 4 different examples. First, for the car suspension. Suppose your input is the road disturbance force, and your output is your car body displacement. For example, like if you driving through the bump, okay, so we have the road disturbance force, and then your car displacement. After you passing through the bump, then you have a displacement. So here is a governing equation. The note is that the car cannot react to the bump before hitting it. Okay, so the motion only depends on the force right now or the force earlier, no future force. So it is a causal system. So this means the y depends on x t minus 1 and so on. Second one is the RC electrical filter. X is the voltage and output is capacitor voltage. Then we have this ordinary differential equation. So this equation is causal. This is the causal system because the capacitor stores energy. For example, your voltage, this is 1 over C I t dt. No, so they stores the past energy. It's better to write past. And then output depends on the current input and also the store of past energy. Well, this is the past inputs, but they cannot depend on the future inputs, future voltage. So for this filter, it is a causal filter. You can also check if you really solve this ordering differential equation, then you will get what is your solution of y. Your y is 1 over RC integration from minus infinity to t, e to the minus t minus tau over RC. Let's write RC minus t minus tau times x tau d tau. So you see that it's from past minus infinity to the current t. Okay. Okay, so you can see that your output depends on your current input and also the past inputs. So here we can say that this depends on your x tau for all tau is less than or equal to t. Right, next example is a temperature control, the thermal system. My input is the heating power and the output is the temperature. So through this ordering differential equation, again that you can find the y. Once you find the solution here, you can see that this output depends only on the current input and the past, because the heater can't affect the temperature before it turns on. So the temperature changes because of the heat now and also the previous heat together. And then for the discrete time case, this one you can see this difference equation easily to see, okay, this is the past input, okay. It's called like a digital moving average filter. This is also filter that you may use that in stock price smoothing or sensor filtering or the audio noise reduction. You'll see this. The system averaged the last 3 measurements. Here's the last 3 measurements. So the output only depends on the previous inputs and the current inputs. Sometimes you may see this as a different form. For this moving average filter, if you see this is like xn plus 1 and xn and xn minus 1. This is also another way, another filter. But for this system, the filter, it is not causal because I have a future input. Okay, and this may also used in the stock pricing smoothing, well, for different purpose. Okay, but this one, this is causal, here not. All right, so let's see another example for discrete time. Okay, I have a system. Input is the delta function, shifted delta function, and the initial condition. So first we have this equation. We have y, this is the output, is equal to xm minus 2 y m minus 1. And then xn is delta function, shifted delta function, m minus 1. And then minus 2y m minus 1. Here with that, the yn equals 0 for all n less than 1. So let's see what is the output yn. most of the time, for the differential equation or difference equation, we guess the solution, or we observe something. Let's see our observation. What is y1? Because we know that y0 is 0. Okay, and the y minus 1 will be O0. Now what is y1? y1 is delta function minus 2y of 0. So that is, what is delta function at 0? That's 1. So 1 minus 2 times 0, that's 1. Then y2 will be a shifted delta function, well, shift of the delta function at 1 minus 2y of 1. So we get, what is the solution here? What is the answer of delta 1? Okay, the hint is, okay, delta 0 is 1. Then how about delta 1? 0, right? Because the delta function, I only have 1 at a 0. Others will be 0. So this is 0. 0 minus 2 times 1. You get minus 2. And how about y3? Del 2 minus 2y2. All right, what is the answer of delta function at 2? 0. So here, 0 minus 2 times minus 2. You get 4. Let's just observe one more. y4, that's delta at 3 minus 2 times y of 3. The delta function is 1 when it is 0. The index is 0. Otherwise, they are all 0. So here, 0 minus 2 times y of 3. So you get 8. According to this observation, we can write it down because you can have like y of 5 and so on. Then you should get yn. So looks like from the observation, what is your yn? 1 minus 2, 4, and here is minus 8. Can you guess like y of 5? What's the answer here? 16. How about y of 6? Minus 32. Good. So we have a pattern here. All right. So for this pattern, 1 and the positive, minus, positive, minus, positive, minus, and it is a power of 2. So here we have minus 1 to m minus 1. And it is 2 to m minus 1 times the unit step function. So which is minus 2 to the m minus 1 times unit function. So you can see that y still depends on the current input. But how do you make sure that this is correct? So to make sure that this is correct, we have the proof by induction. So for the proof by induction, we have 2 steps. The first, we have to show the initial case, and then show the pattern holds for some n. Later on, you show the inductive case. Okay, to show that if pattern holds for n, and then how about the n plus 1? So first, let's see the initial case. So the first the first one we have already shown that. Okay, for example, n equals 1, and then the y of n is minus 2 to the n minus 1, which is 1. Now for the second one, okay, we need to assume like yn equals minus 2 to the n minus 1. Okay, so assume that this is correct. Then we want to show y of n plus 1. So y of n plus 1 should be minus 2. n plus 1 minus 1, so it should be n. So here should be n. And we know that actually y of n plus 1 is equal to delta n. n plus 1, n plus 1, so here minus 2 of n. Minus 2 times y of n. So it is 0 minus 2 times minus 2 to the n minus 1. That is minus 2 to the n. So it's correct. Right. Now let's take a break, and then later on we are going to talk about the response to the complex exponentials. Okay, so let's see the response of a linear time invariant system. Now my input is complex exponential. This is continuous time. This is discrete time. Okay, so for the complex exponentials are the eigenfunctions. So you can see that for the linear time invariant system, remember what input we have, then my output is, the form is similar to your input. So for the continuous time, if the input is complex exponential, and we can say this is like a eigenfunction, or you'll see y. Okay, so if I send it to the LTI system, what is the output? And for the discrete time case, this is our input. Then if I send it to the LTI system, what's the output? My input is exponential. I expect that the output should be also exponential, complex exponential. Okay, so here we have e to the zt. And for discrete case, z to the n. This is your output, but it can't be just exactly the same. So we have this input times something. So here we have h of z or f of z. Okay, if my input is complex exponential, my output is also complex exponential times something. just like here. This is my input, and here my output will still have the same form. Here I have input and output, input and output. Don't you feel like this is familiar to you? Like in linear algebra, a vector times a matrix will be the eigenvalue times your vector. So those like a vector. And this is your eigenvalue. So this is your eigenfunctions. And here is your eigenvalues. Okay, so same thing. Here the V is the eigen. Here this is eigenvector. And then the eta is the eigenvalue of the matrix A. So eigenvalue of your matrix A. So for the LTI system, again, if we have an input, then we expect that our output is in the same is in the same form, but with a multiple or a constant or with a coefficient. For example, if my input is e to the t, then the output y is equal to your system times convolve your input. Okay, in this case, if you use the formula, there'll be to h tau, and x is e to the t, so e to the t minus tau, d tau. The dummy variable is tau, so I can put e to the t outside, and then the integration h tau e to the minus tau d tau. This is your output. And for your output, let's see, it should be red. What is the integration? This here. After the integration, this integral on the red line will be just a number. So my output is e to the t but times a number. So e to the t to the LTI system I'll have a constant times e to the t. So in general, so more generally, e to the zt, and I send it to an LTI system. What do you expect about the output? I should have z to the e to the zt times a constant And what is constant here? This constant is the integration h tau e to the minus z tau d tau. And we say this is like a system response, h of z. Similarly, then we can apply this to the discrete time case. For the discrete time case, if my output is z to the n, so here is my input, say z to the n, send it to the LTI system. Then have an output. So since it is an LTI system, the output is the system convolved your input. So that's the system convolve z to the n. And that is summation Now let's plug in the x. We have next line. Summation h, and your x in m minus k to be z to the m minus k. And since this is the summation with respect to k, we can put z to the n outside. And then summation. Okay. And for this summation, it really depends on your z, right? If your z is less than 1, the ratio is less than 1, then you have a final sum. So here is f of z, and this is the number depends on z. For example, if my z, while the input is 1/2 to the n, to the power n, send it to the LTI system. What is the output? So, because this is LTI system, so we know that the output, the form is very similar to your input. So it should be 1/2 to the n. Okay, same thing, and you times something. Okay, so here, this something is k from minus infinity to infinity. hk 1/2 to the minus k. So we can have more inputs. Okay, like a linear combination of your complex exponentials. So suppose the x is 7 times complex exponential, 8 times e to the minus t, and plus 9 times e to the 3t. What is the output? So the x send it to the LTI system. So the output, yep, so for the output, since I have an input 7 times e to the jt, I expect my output should have also 7 times e to the jt times something, and also 8 times e to the minus t times something. Okay, so here I should have 7. What do we use? Maybe the green one. H times e to the jt plus 8 times h, that's minus 1, e to the minus t, and 9 h 3 e to the 3t. And what is h? So for h is the system's response. Another example, if my input is cosine t plus sine t, what is the output? From this example, you see that if we have a complex exponential, then I should have complex exponential at the output times a constant or times the eigenvalues. So here we can rewrite the cosine and sine into the complex exponential form. That is e to the jt plus e to the minus jt divided by 2 plus e to the jt minus e to the minus jt, that's sine, divided by 2j, that's sine t. So here we have complex exponential, e to the jt 1 minus j divided by 2. And e to the minus jt 1 plus j divided by 2. This is our those are our two inputs. So my output can be expressed or expected as sent into the LTS system. So I have two forms. I put it here, and times the system response. So here 1 minus j divided by 2. Then we times h j e to the jt, and 1 minus j one plus j over 2 h minus j times e to the minus jt. And you can see that if I have a bunch or a linear combination of your complex exponentials, then here we have more. Well, if we have more here, then we will write it down a lot. And sometimes we say it's pretty handy to express the input. So that's why that we can use the Fourier analysis to do it. Okay. Where's my ID? Okay, so let's see the Fourier analysis. Now x is the continuous time periodic signal, and t naught is the fundamental period. The fundamental frequency, if we have a fundamental period, then fundamental frequency will be just 2 pi over t. Okay, that's omega naught. X is a continuous time periodic signal, and then can be expressed as a linear combination of the complex exponential. Then for the coefficient, how do you find the coefficient? Again, x is 5i plus 4j. To get the coefficient, x in the product I. And then for the function in the product, function in the product will be the integration. See, the inner product will be the integration and doing the conjugate. Okay, so here we do the integration and the conjugate. So x times here, doing the conjugate, and that's why we have minus psi. Now for the integral, it's just one period, okay, from 0 to t, or t over 2, or minus t over 2 to t over 2, just one period, and divide by your period. Okay, so again, you see that to get your coefficient, your x in the product, your basis. But for the function that you need to do the conjugation. For example, if my x here, and then this is ak, we need to find ak. Actually, if x is the input, well, just the signal is here, then what is the ak? So to find the ak, should we have to do the integration every time? We can rewrite our signal x. Since it is cosine and sine, I can express cosine and sine by using the Euler formula. Then it can be expressed in terms of the complex exponential. So 3 cosine 3t means e to the 3jt plus e to the minus 3jt divided by 2. And then 1 plus 6j sine 6t will be e to the 6jt minus e to the minus 6jt divided by 2j Now just rearrange this. Okay, we can write it down. It's 3 over 2 e to the j 3t plus 3 over 2 e to the minus j 3t plus 1 plus 6j over 2j times e to the j 6t and minus 1 plus 6j over 2j, this times e to the minus j 6t. And this is already a linear combination of your complex exponentials, right? I can even write it down. This is the summation ak times e to the j k omega naught t. So what is ak? What is a1? 3 over 2, right? So this is a1. This is A1. And how about A2? Here, this is A2. And now we need to move on. This is A minus 1. And then here, overall, this is A minus 2. There's no A naught. Okay, A naught, that means that A naught is 0. So A naught is 0. A1 equals A minus 1, that's 3 over 2. And then A2 is equal to minus A minus 2. 1 plus 6j over 2j. And all others, AK is equal to 0. So for this example, like sometimes you don't have to really do the inner product or doing the integration. Okay, by observation, you can get the coefficients. Now, let's see. Let's have some observation. A periodic signal, so a signal periodic in time t, can be represented equivalently by an infinite vector. Okay, we can just use this. Well, I think it should be here. We can use this to express our signal. Okay, just like here, we express the signal like this, then we know that actually the signal should look like this entire form, just in using the coefficient. Next, we want to learn that if I have two different frequencies, x is cosine omega 1t plus cosine omega 2t, is x this signal periodic? Or what kind of conditions can say that x is periodic? First, if I have a cosine omega 1t, what is the period? Oh, we know cosine is a periodic signal, right? So if I have cosine omega 1t, what is the period? The period is 2 pi over omega 1. And here, the period is T2, that's 2 pi over omega 2. I have my own period, you have your own period, okay. But overall, if I want to say that this is a periodic signal, I need to find the common things here, right? So for the period t, the period t of the signal x must be such that t omega 1 should be 2 pi n for some n that's in a complex number or in integer. And also t omega 2 should be 2 pi m for some m in m belongs integer. So in this case, if T1 divided by T2 is irrational, then x is not periodic. So x is non-periodic. If this ratio is rational, T1 over T2 if it is rational, then X is periodic. And they should have like M T1 should be equal to N T2. For example, if I have a cosine 3t and sine plus sine 7t, what is the period? If x is a periodic signal, what is the period? First, let's see cosine 3t. That means omega 1 is 3. So the period t1 is 2 pi over 3. Sine 7t. So omega 2 is 7. And then t2 should be 2 pi over 7. So overall, t1 over t2 is 7 over 3. Rational, so the period should be 3t1 or is equal to 7t2, and actually that's just 2 pi. Another example, we can use the continuous time Fourier series coefficient formula to find the coefficient. Okay, here's the formula. For example, if I have a rectangular pulse train, so if I have a rectangular pulse train, so the rectangular pulse train looks like this one. This is minus 1/2, 1/2. The attitude is 1. First, we need to find the period. Okay, this is a periodic signal. Then what is the period? Fundamental period. T equals 2, which means the fundamental frequency is 2 pi over 2. That's pi. So your coefficient is 1/2 or 1 over 2, 1 over t, from minus 1 to 1. X, and in the product, your basis. You have minus 1 over 2jk pi e to the minus j pi over 2k minus e to the minus j pi over 2k. But normally that we won't use the formulas. We use drawing. So in the rest of this semester, you will draw a lot. You will plot the figure, because when you plot the figure, that's easier to figure out your coefficients. And we do have to do some integration while using the integration, but well, you will see. Okay, so here we just talk about the continuous time Fourier series. Let's just talk about this continuous time Fourier series. For a periodic continuous time signal, we can also express this periodic signal by Fourier series. So remember that for periodic continuous time signal, we can express our signal using Fourier series. If your signal is periodic, okay, and here's a coefficient. And again, that from these two equations, you can see that how do I get the coefficient? Your signal, inner product, your basis, right? The vector inner product, the function inner product. So that's why we have the conjugation here. So to get your coefficient, just do the inner product. And then you integral over a period, any single period. So here, integral over any just single period. Again, if your signal is periodic, if not, what should we do? If not, then we take the Fourier transform. Okay. For discrete time Fourier series, for discrete time, again, that the signal is periodic. Again, this is a periodic discrete time signal. The fundamental period is n. Then your signal can be expressed, a linear combination of your bases. But this is only from 0 to n minus 1. And how about your coefficient? Again, your coefficient, x times are here. Similarly, this omega naught, I'll write it down, the omega naught is 2 pi over n j. First, this should be j. Okay, so here is 2 pi over n. So again, you see that I have my vector in the product, your basis, but we do the conjugation. Okay, and this time is, why do we only need n turns? Well, you can think about this question during the break. So why do you need only n turns? Let's see this exponential term. Okay, for this exponential term, and n is just the integer. So e to the j k 2 pi over n lowercase n. When n equals 0, what is the result? E to the 0, that's 1, right? But when n equals capital N, j k 2 pi over n, when this lowercase n is equal to capital N, they cancel out. E to the j k 2 pi is what? Cosine 2 pi plus I sine 2 pi. Cosine 2 pi is 1. So that's why they are equal. And ejk 2 pi over n. So this term, if I plus, actually this exponential is equal to 2 pi over capital n times k plus capital N, because this is e to the j 2 pi over n lowercase n, and the other one, they will cancel out, so everything will be 1. So we do the integration summation from 0 to n minus 1, not n, because it's like a cycle back to the original point. So for example, if I have the signal, discrete time signal, periodic, okay, it's a sine 3 pi n plus pi over 2, then what is your coefficient? AK. For this one, sometimes we don't really want, well, if you want to use the formula to solve the question, that is the least option. Okay, you couldn't find any other methods. Okay, fine, then we use the formula. Otherwise, we don't use the formula. Okay, we try not to use the formula, because we always have some better way to find out. So here, let's just observe again, x 0, that's sine pi over 2. What is sine pi over 2? 1. x1, that's sine 3 pi plus pi over 2. How much is it? 7 pi over 2. Sine 7 pi over 2 is, you should either guess 1, 0, minus 1, those 3 options, right? 1, minus 1. X of 2, you have a sine 6 pi plus pi over 2. That should be how much? 1. Okay. x3, similarly, okay, and you'll get this is minus 1. So, what is the fundamental period? You can do that x of 4, 5. Then you should observe that what is the fundamental period? That repeat that again. The value repeat that again. So 6 pi. No, the fundamental period. Like, now here is like 1 minus 1, and then you go to 1. Like 1. Oh. 1 minus 1, 1 minus 1, 1 minus 1. Yeah, so the period, fundamental period is 2. So here, fundamental period is 2. Then the frequency is pi, fundamental frequency. And then A naught is 1 over 2 when n from 0 to 1 xn. If we use the formula, then we remember that it should be the signal in the product, their corresponding basis, And then you do the summation for 1 period. And 1 over your fundamental period. So here it should be e to the minus j 0 pi n. So that is 1 over, actually it is 1 over n, doing the average. Okay, so here is the average from 0 to n minus 1 x n. So this is the average signal. And this value is over 1 period. So this is 1/2 x of 0 e to the j 0 plus x 1 e to the 0. That's 0. And A1. That's 1/2 x 0 e to the 0 plus x1 e to the minus j pi. That's 1. So the signal x that's ak e to the j k pi n. It should be a1 e to the j pi n plus there's no a naught, so this is also equal to e to the j pi n. So e to the pi j to the n, and that's minus 1 to the n. Alright, so sometimes we can also solve these coefficients by inspection. Okay, again, that because this is a sine, we can express sine into using the Euler formula to get it. And then, so here, you can also see the tables. So here you can see the table of continuous time Fourier series and also discrete time Fourier series. So you don't really have to calculate, just check the table. Alright, let's quickly see this example. I have a discrete time signal, x. They have to satisfy the following things. X is periodic, and then the fundamental period is 6. And for this summation, that should be 2. Like an average is 2, not yet. This summation is 2. And also this equation. And the x has the average power. Then we need to find x. So by the first one, x is periodic with 6. The fundamental period is 6. So by the first hint, x is the summation from 0 to 5, ak, e to the j, k, n is 6, right? So 2 pi over 6, that'll be, well, a pi over 3. So here will be pi over 3, n. Then the coefficient is 1 over the fundamental period, and then you do the inner product. Inner product, your signal inner product with the basis with a conjugation. N is from 0 to 5. So A naught, it's 1 over 6. Now this is the moving the average of the signal. Okay, and this should be 1/3 because it is by the second hint. Now by hint 3. For hint 3, let's see, by 3, this is a summation from 2 to 7, 2, 3, 5, 4, 6, 7. So it is also like a period. All right, minus 1 to the n, xn. How can we express the minus 1 in the complex exponential form? Minus 1 is e to the minus j pi over 3 times 3 to the n xn. Correct? So this will be n from 2 to 7, x, and then e to the minus j pi over 3 times 3n. Well, x is periodic, so the summation from 2 to 7 is also equal to the summation from 0 to 5. And this is equal to 6 times A3, and that's 1. So A3 is 1 over 6. The last one, the power, the average power. 1 over 6. N is 0 to 5. Okay, this NH is 5 over 36. That is from the hint. This is equal to your coefficient square. That is A naught squared plus A1 squared plus A2 squared plus A3 squared and A4 squared also A5 squared. We know A naught, we just find, where's A naught? Oh, here. A naught is 1/3. So this is 1/3 square. And A3, we found that it is 1/6 square. So overall, if we add these two, it is already 5/36, which means those are all zeros. I only have A naught and A3. And therefore, the x is A naught plus A3 e to the j pi n, which is 1/3 plus 1/6 times minus 1 to the power n. Okay, I think I haven't mentioned that for the possible theory. Okay, so the possible relations for the periodic signals. Okay, so that's why the signal's power, you can also do it as the summation of your coefficient square. Okay, so that's why this one equals all the coefficients magnitude squared. Right, next one. Remember that if we have what input we have, send it to the LTI system. My output should have the same form of your input times something extra. So if this is e to the st, and I send it to the LTI system, then I also should have e to the st, but I times something. Here is h over s, and this h over s is this form. For example, e to the j pi over 2 t, send it to the LTI system. Then we should have like h is j times pi over 2. And we still have the input e to the j pi over 2t. And the h, j pi over 2 is, we call the h is the frequency response. Then if my input is a combination of your complex exponential, then after going through the LTI system, your output should be also a combination of the input. And this is the coefficient This is a coefficient. We can rewrite that to bk and e to the jk omega naught t. That is the output. So you can see the input and then output. The h omega or hj omega, while in different textbooks they have different notation, but overall they just call frequency response, and your ht is the impulse response. All right, today we have to finish 2 more pages. 2 more pages here. If I have a signal, okay, it's a sine function. Okay, I can represent this into the complex complex exponential. Okay, so in the complex exponential, then actually we just have e to the j 800 pi t and also e to the minus j 800 pi t. So what is the fundamental frequency? The fundamental frequency should be 2 pi 400. So your fundamental period is 2 pi over omega naught. That is 1 over 400. And you can see that this 1 over 2j is A1. And this with minus sign. Here this is A minus 1. So when the x send it to the LTI system, we expect the output is the AKH 2 pi 400 K e to the j 2 pi 400 T. That is, if we expand this summation, we should get 0 for A naught, and then minus 1 over 2j, that's, oh no, this is A minus 2, and here's A minus 1. And then A naught, and A1. E to the j 800 t pi t. The output is just with A minus 1, with A minus 1 minus 1 over 2j h minus 800 pi e to the minus j 800 pi t. And then A1 e to the j 800 pi t. Now we have already known that the input and the output is similar, except there's the frequency response, this h omega. Let's talk about the h omega. Okay, we have different forms of h omega. So if the h omega looks like this is minus 800. Here is h omega 800. And now I have here is minus 1000 pi and 1000 pi. Magnitude is 1. So in this case, let's see the output here. If my h is this, okay, h is this, a filter, right? It's greater than 100 and minus 100 pi. So they include this. So this one is 1. Here is 1. Right. In this case, the y, I can put here. Your output y is minus 1 over 2j times 1 times exponential minus j 800 pi t plus 1 over 2j e to the j 800 pi t. And this is exactly the same as your x. This is equal to x. So that means I send the x to a system and I get y. So the x and y are the same. This system is like a filter. They just pass the signal. They pass the signal without changing anything. But if the h is this, so it's still magnitude 1. Too late. Okay, but this is okay. H. This is 1, but it's minus 500 pi and 500 pi. Otherwise, they're all 0. So here it's 0. Day. Then what is the output? That's 0. So the output is 0. So this filter or this system annihilates the x. Annihilate x. And how about this frequency response? So this is 1000 pi. In this case, I only pass the A1. So this is 1 over 2j e to the j 800 pi t. So here the system is kind of like a filter design. You have a different filter. I can let any signals going through either pass all the x or just delete, avoid x to pass, or you pass part of them. Okay, so here is a question. If a system that my input is 2 pi 400 t, but I want to get the output, and then we get the output 2 pi 800 t, can the system be LTI? Like the frequency is 400 and then the output becomes 800. This couldn't be the LTI system. Because for the LTI system, what input you have, your output should have the similar form. So the frequency should be the same. And here are some properties for the Fourier series. Linearity first. X and Y are two periodic signals with the same period. So with the same period, the xt, okay, I will get the coefficient. So this is continuous time Fourier series. I get AK. And then YT with the same period, with the same period here. CTFS. I have a BK and that's the coefficient. Then the linearity says that if I combine these two signals with a different coefficient, then their coefficient is also the linear combination. So here will be alpha, here's beta. So the linear combination of signals will produce the same linear combination of their Fourier series coefficients. And for the time shifting, if the coefficient for the x is ck, then if I shift, I have a time delay, t minus t naught. If I have a delay, what happens of your coefficients? You have e to the minus j k omega naught t naught ck. And then the t naught is a real constant. And what do we say from this property? You see that the coefficient is still here. If I take the magnitude, okay, this is like a phase change, but my magnitude is still the same. So when we do the time shifting, then we only change the argument, okay, the phase, not the magnitude. So the magnitude should be the same. Well, the coefficient should be the same with the magnitude. Time reversal. So xt, the signal with the coefficient ck, then if I reverse this signal, so minus t. Then my sequence, or my coefficient, what happens? They also reverse. You can prove that, which means that for xt, I have a3, x minus t, then a3 becomes a minus 3. So they just reverse. You don't have to calculate the coefficient again. They just have like a a1, a minus 3, a minus 2, a minus 1, a naught, a1, a2, a3. And you reverse it. This go here, and this one here. They just reverse your sequence. Conjugation. If I do the conjugation, x conjugate, then your coefficient, what happens to your coefficient? Do you have to calculate that again? No, it's just conjugate, but also we have a minus. So you flip and then do the conjugation. So the conjugation thing, a signal, then I have an effect on the time reversing and also conjugating the coefficients. And then time scaling. If I have a time scaling, what happens? The coefficients are also the same, okay? But we have a new time, a new period from t to t over a. Okay, so if a is 2, I compressed. So I have a period t, but if I compressed, my new period will be t over 2. You can plot one signal, discrete time signal, then you can observe. This one, very important. You should have a mark, okay? Differentiation. If you take the differentiation, what happens? You have a new coefficient. This is a new Fourier series coefficient. Okay. Even though you take the differentiation, well, here is the same, but you just have a new coefficient. We will see the example next week. And then next week, you are going to learn some basic Fourier series. Okay, what is a periodic train of rectangular pulses? And also periodic train of delta function. And also like something very important, signals that we may use. Okay.